What we'll do now is find the solution of the state space description. X dot is equal to ax plus bu, y is equal to cx plus du, and we'll start by finding the solution of the state equation. Okay, and we'll start with a simplified version of this state equation. We'll take the homogeneous system here. X dot is equal to ax, which means that we consider that the input is 0. And well, you have seen this, but for simpler systems the solution can be written in terms of the exponential of this element. In this case, A here is a matrix, and we'll come back to this notation, exponential of AT, where A is a matrix, later on in the course. So the general solution is exponential of AT times a constant K. It's quite easy to see that this is indeed a solution. The derivative of x dot will involve the derivative of this one, and well, this is what you obtain. So x dot will be this derivative that you've got over here times k, right? But you can see here that this is x of t, so indeed x dot is ax as is written over here. So indeed this is a solution of the homogeneous system that is given over here. So we've just seen that the solution of the homogeneous system x dot is equal to ax is the exponential of at times a constant. So the question is, what is the constant? Well, if we have initial conditions in t0 and that xt0 is x0 with x0 known, well, then if you plug t0 in here, well, you have this quantity that is equal to x0, and you can kind of compute k. And if you inject k in here using the properties of the exponential, you find that the homogeneous solution is written as follows. Okay, so this is the solution to the system x dot is equal to ax with x t0 is equal to x0. So we had considered the homogeneous system x dot is equal to ax, and we had found that the general solution of that is the following. Okay, so this is the general solution of the homogeneous equation or the homogeneous system. Of course, we are interested in the non-homogeneous system. So what we'll do is something that we've seen before in previous courses. We'll use the method of the variation of a constant, right? The solution that we had for the homogeneous system was exponential of at times k, right? And if we use the method of variation of a constant, this is the solution that we propose for a particular solution, at least of the non-homogeneous system. Okay, so you remember that the non-homogeneous system will have as solution the solution of the homogeneous system plus a particular solution of the non-homogeneous system. So what we'll do now is find this particular solution of the non-homogeneous system. This is the solution that we propose using the method of variation of a constant. We have to plug it in, so we need to compute x dot, so we need to compute the derivative of a product. So this will be the derivative of the exponential times k, first term, plus the exponential times the derivative of k. So this is k dot. Remember that this is x of t. So this is a x of t, and the term that you've got over here. And therefore the second term must be bu of t. Okay, so this allows us to compute the derivative of k, and we can obtain k as follows by integration. Okay, so if we plug this in here, we'll have x of t is equal to the integral from t0 to t. Okay, this one we can bring into the integral because we integrate with respect to tau. So we'll have the exponential of a t minus tau b u tau d tau. So this is a particular solution of the non-homogeneous system, and if we add it to the general solution of the homogeneous system, we have the solution of the state equation. So this is the particular solution to the non-homogeneous system, right? This is the general solution of the homogeneous system, and if we add the two, we have the overall solution of the state equation. Okay, we are interested in the solution in terms of the output, so we have to introduce the output equation. Y of t is cx of t plus du of t, and this is how we end up with this output equation. So if we forget about the feed-through terms, remember that in reality, in practice, for physical systems, this direct feed-through term will disappear. We can make the links with stuff that you've seen in previous courses. This is the zero input response, la réponse libre in French, and this is the zero state response. So this means la réponse forcée in French. And this is also a convolution integral, so this quantity here must be h t minus tau. So h of t, the impulse response matrix, is c exponential of a t b. Well, suppose that you're at time t is equal to t0 and you want to compute future outputs, and that this means t larger than t0. What you need is x0. Okay, so the state at time t0, and this is why we can say that the state vector acts as a history accumulator. It accumulates everything that has happened in the past, and what you need is future inputs for t larger than t0. What you do not need is the input history. You don't need the inputs before t0. As mentioned before, this first term here is the free response. I've often called it the zero input response, and this term here is the forced response or the zero state response. These two terms, free response and forced response, make the link with the terms, or how it is said in French, réponse libre et réponse forcée. So it is time to come back to this quantity exponential of a t that we can also call phi of t, which is the state transition matrix. Okay, so this might look a little bit strange, but you can define it, this quantity, using a Taylor expansion. Remember that the Taylor expansion of the exponential in the neighborhood of 0 is 1 plus x squared over 2 plus x cubed over 3 factorial, and so on, right? Well, in the same fashion, you can define the exponential of at. It's an identity matrix plus at plus a squared t squared over 2 factorial, and so on. So now what you can do is compute the derivative of this exponential of at with respect to t, and what you'll have is, well, this will not give a contribution. This is a, you'll have a square t, and so on. And if you look at it, it's a times an identity matrix plus a t plus, and so on. So what you have here is that the derivative of this one is a times the exponential of at. So this is a formal proof of what we have used before. Okay, so this is what is written over here. This simply says that the exponential of a0 is the identity matrix. This says that if you multiply exponential of at and the exponential of a tau, what you obtain is the exponential of a t plus tau. And this says that e minus a t, right, is the inverse of this quantity over here. So this will be the identity matrix. Well, in the next few slides we'll make the link with the other course in the teaching unit Advanced Control 1, which is linear algebra. Well, this is because we need to compute the exponential of at, and we'll see that there are, well, several methods to compute this exponential, but do not forget that you can also use the definition that is given over here. Okay, it might now not look very handy because it has an infinite amount of terms, but for some matrices, for instance, A is equal to 0, 1, 0, 0, this might come in handy, because if you look at a squared, which is 0, 1, 0, 0 times 0, 1, 0, 0, you will see that this is the zero matrix. Okay, so for this matrix over here, the exponential of at is simply the identity matrix plus 0, 1, 0 times t. So we have 1 t 0, 1, and it's actually the easiest method to compute the exponential for that type of matrix. So we'll see other methods to compute the exponential, but please do not forget that in some cases the Taylor expansion definition can be used to compute the expression of the exponential of at. So here's a summary of things that we've seen in the course Linear Algebra in Applications. How to compute eigenvalues and eigenvectors. Remember that an eigenvector is a vector such that its image by A lies in the same direction, right, or is parallel. It's same direction if lambda I is positive, and opposite direction if lambda I is negative. But anyway, the image of vi is parallel to Vi itself. This is the definition of an eigenvector, and of course you can rewrite this in this fashion. And for this system of equations to have a solution other than the trivial solution Vi is equal to 0, of course the determinant of this quantity must be 0. So this is how you find eigenvectors. Well, you find the solution to this equation here. Okay, this is the characteristic polynomial, and this allows you to obtain the eigenvalues, which are the roots of the characteristic polynomial. And once you have the roots, you can use this equation to find the associated eigenvectors. We have seen in the course of linear algebra and applications that if a matrix has distinct eigenvalues, in the sense that the lambda 1 to lambda n are all different, then the matrix A can be diagonalized. So what you have to do is put the eigenvectors and that correspond to these eigenvalues in a matrix V. Okay, you stack them right next to the other, right, and you obtain a matrix V. And then if you compute V minus 1 AV, you'll have a diagonal matrix with on the diagonal the distinct eigenvalues. If the eigenvalues are not distinct, in the sense that there are some eigenvalues that are equal to one another, then it's not necessarily the case that you'll be able to diagonalize the matrix A. When A has multiple eigenvalues, in general A cannot be diagonalized, but what can be done is to bring it in the Jordan normal form using a similarity transformation V here. And V is composed of what is called generalized eigenvectors. Well, this Jordan normal form is a block diagonal form, and on the diagonal you find Jordan blocks, which are square matrices of the form that is given over here. So you have the main diagonal, and on the main diagonal you find the eigenvalue, and on the diagonal above you have all ones. We'll see later on in the course how those Jordan blocks appear in state space descriptions of systems. In the exercises and at the time of the exam, I don't expect you to be able to bring a matrix A into its Jordan normal form. We will only work with matrices that can be diagonalized. In the Jordan form, the geometric multiplicity of a given eigenvalue is the number of Jordan blocks it appears in. The algebraic multiplicity, again for this given eigenvalue, is the sum of the orders of the Jordan blocks it appears in. And if the matrix A is diagonalizable, then its geometric and its algebraic multiplicity must coincide. This means that every Jordan block has size 1. So we have used the characteristic polynomial P of lambda to compute the eigenvalues. It's a polynomial in lambda of degree n. Okay, and it's associated with the matrix A. What you can do is define a matrix polynomial on this characteristic polynomial, and what you do is replace the variable lambda by the matrix A, and where there is no lambda, such as here, you have to introduce an identity matrix. And what the Cayley-Hamilton theorem says is that this polynomial constructed on A is the zero matrix. Okay, so this result in itself is not that important, but what is important is that you can construct a matrix polynomial here on this characteristic polynomial. And later on what we'll do is that, for instance, if f of lambda is e to the lambda t, what you can do, and this is not a polynomial function but simply a function, you can also construct a matrix function which is e to the a t, and what we have done is replace lambda by a. Well, the results that are on this slide will allow you to compute the exponential of at using the Cayley-Hamilton method. Okay, so let us assume that we have a matrix A with distinct eigenvalues lambda 1 to lambda m, and each of these eigenvalues has a given multiplicity n1, 2, and m. Then take two functions, f lambda and g lambda. They are not necessarily polynomial. We say that these functions, f lambda and g lambda, are equal on the spectrum of A if the following relations hold. Okay, so they must be equal on the eigenvalues, and if the eigenvalues have a given multiplicity, they must be equal also on the derivatives. So let us take an example of a matrix that has three eigenvalues. So we have L1, okay, it is eigenvalue 2 times, so it means that the multiplicity, the algebraic multiplicity here is 2, and then we have another distinct eigenvalue which will be 2, and this one has a multiplicity of 1. Okay, then we can say that f lambda and g lambda are equal on the spectrum of A if f of 1 is g of 1, the derivative of f with respect to lambda evaluated in 1 is equal to the derivative with respect to lambda evaluated in 1. Okay, and then we have f of 2 is equal to g of 2. There are three conditions because there are three eigenvalues, well, because one eigenvalue is double here, it has algebraic multiplicity 2. So if these conditions are satisfied, then f and lambda and g lambda are equal on the spectrum of A. Well, we have this property that if f lambda and g lambda are two such functions that are equal on the spectrum of A, then the polynomial function, okay, evaluated on A with f and g are equal. So we have f of A is equal to g of A. So this will be used, for instance, to compute e to the at, and so what we'll do here is compute or use the function e to the lambda t. We'll design a polynomial function. This one will be polynomial. We'll find a function g of L that is equal to f of L on the spectrum of A, and then since f of A, well, that's e to the at, is equal to g of A, we'll have a means of computing this exponential. So we now talk about methods for computing the matrix exponential e to the at. Remember that e to the at has been defined using a Taylor expansion. Okay, so of course there are an infinite number of terms, so in most cases this definition is, well, difficult to use. But remember that sometimes you have matrices that are such that for some power n, an is equal to the 0 matrix. Okay, so there is in this case then only a finite number of terms in this Taylor expansion. Okay, which means that in some cases the Taylor expansion can still be used to compute the exponential of at, and I've given you an example previously. If this Taylor expansion cannot be used because there is an infinite number of terms, there are three other methods that you can use. The first one is the Laplace transform method. The second one is the Jordan decomposition method. It involves diagonalization, and the third method is the Cayley-Hamilton method. Some additional information here. If there exists an n such that an is equal to the 0 matrix, then obviously an plus 1 will be the 0 matrix, an plus 2 will be the 0 matrix, and in fact every power higher than n will be the 0 matrix. This is why this Taylor expansion reduces to a finite sum. Well, the reason why we spend so much time on the computation of the exponential of at is that, of course, this quantity intervenes in the solution of the state space system. We will also see later on in the course that the quantity exponential of ats will be used when we discretize the system, when we obtain a discrete time state space description of the system. Here ts is the sampling period. Okay, so this matrix will also be important. When we discretize, there is another matrix that is important. It's rather obvious. When you have exponential of at and you write t is equal to kts, what you will have is exponential of ats, this is this matrix here, to the power k. So in discrete time, taking a matrix to the power k plays the same role as this exponential of at. So this is also very important to be able to do this. And the second method and the third method here will also allow you to take the power of a matrix. So this is how you can obtain the matrix exponential using the Laplace transform. We have seen that the derivative of the matrix exponential is a times the exponential itself, and remember that the Laplace transform of a derivative, let's take for instance dy dt, is sy of s minus y 0, right? So what you can do is take this equation and take the Laplace transform on both sides. So we have the Laplace transform of the derivative of the exponential, so that's the exponential here derivative, and on the other side we take the Laplace transform of this one. We have a times the Laplace transform of the exponential. Okay, so this one can be rewritten like this using this expression over here. So s time the Laplace transform of the exponential minus y0, that's the exponential evaluated in 0, and we have seen that this is the identity matrix. So using this equation over here and reorganizing things, you obtain this equation over here. So the Laplace transform of the exponential matrix here is s times the identity matrix minus a, the whole thing inversed. Okay, so to obtain the exponential of at, you first compute the inverse of si minus a, and then you take the inverse Laplace transform. The second method to compute the exponential of at is to use the Jordan form. Remember that if a is diagonalizable, then we can obtain a diagonal matrix lambda by doing the following operation. Okay, v minus 1 av, and in v we have stacked all the eigenvectors. So equivalently, this means that a is v lambda v minus 1. Okay, so how can we obtain this result here? We know that the exponential of at, that's the identity matrix, plus a t plus a square t square over 2 plus etc. Remember, this is this Taylor series decomposition. So what we can do is rewrite things a little bit, and we write it as follows. The identity matrix, we can rewrite it as v minus 1, and what we can do over here is write a as v lambda v minus 1, that's a times t, and for this the following term we can do something similar. So this is a, by the way, and this is what we have written over here, and we have something similar over here, v lambda v minus 1, that's a. We have a squared, so we have a times a, so we have v lambda v minus 1, that's a, so we have a square here times t square over 2, and we can continue. Okay, so the v minus 1 and the v will cancel out, and you will always have v in front and v minus 1 at the back. So you can rewrite this as v times something. In this case it will be the identity matrix, because at the end here I'll multiply by v minus 1, and here I'll have lambda t. The following term will be lambda squared t squared over 2, etc. Okay, so, and this thing here is, well, the Taylor series decomposition of e to the lambda t, and this is this thing over here. So what you do, you have to compute the eigenvalues and eigenvectors, okay, and then you compute this matrix here, e to the lambda t, and you pre-multiply by v and post-multiply by v minus 1, and you obtain the exponential of at. If the matrix cannot be diagonalized, you have a same expression, of course, but I do not expect you to be able to do those kind of calculations. You have the same expression, and here we have on the diagonal, well, blocks. So this matrix here becomes block diagonal. So we have seen in the previous slide that if a is not diagonalizable, e to the at is v times v minus 1, and here on the diagonal you have the exponential of Jordan blocks. Okay, remember that the Jordan block is such that on the diagonal, on the main diagonal, you have the eigenvalues, okay, and on the diagonal just above you have ones. And what you can show, and we'll see this in an example, is that this exponential of Jordan blocks, well, you have the appearance of terms that are just like in the case where the matrix is diagonalizable, so e to the lambda it, but you also have the appearance of terms that are e to the lambda it times t and e to the lambda it with higher powers of t. It all depends on the size of this Jordan block. We'll come back to that later in a more practical example. The third method for computing the exponential of at is to use the Cayley-Hamilton method. So the first thing that you have to do is to compute the eigenvalues, and we'll assume here that there are n eigenvalues. And then you have to find a polynomial, okay, that is such that it is equal to this function here on the spectrum of A. Well, to be equal to this function on the spectrum of A, this will lead to n conditions. Okay, so what we'll have to do is take a polynomial g of lambda of degree n minus 1, so there will be n coefficients. Okay, this is what we need because we have n conditions, so we'll be able to compute the n coefficients alpha I. Once we have found a polynomial g lambda that is equal to f lambda on the spectrum of A, we can use this equation here to compute the exponential of at. Remember that the function constructed around the matrix A is equal to the exponential of at. We simply have to replace the variable lambda by the matrix A, and this exponential of at will be equal to g constructed on A. We have to take this polynomial here, replace the lambdas by the matrix A, and where there is no lambda we have to include the identity matrix. So let's start some exercises with the diagonalization of a matrix A. So the first thing that we have to do is to compute the eigenvalues and eigenvectors. So these exercises are also covered in the other part of the teaching unit Advanced Control 1, which is linear algebra and applications. So go and have a look. It will go even further in the computations of eigenvalues and eigenvectors. So here the characteristic polynomial is constructed. In the notes in the slides I have probably lambda I minus a. Here I have constructed a minus lambda I. It's a little bit easier here, but of course this is the same thing up to a change of signs. So you can either choose a minus lambda I determinant or the determinant of lambda I minus a. The eigenvalues will remain the same, of course. Here the characteristic polynomial can be computed using this determinant, and you can see that the characteristic polynomial is given over here. There are three eigenvalues, minus 1, minus 2 and minus 3. So in this case the matrix A can be diagonalized. So we'll start with lambda 1 is equal to minus 1. So what we'll do is write a minus lambda 1 I times v1, and in this case this will be minus 1 minus 1 0 0 0 0 0 1 minus 2 times v11 v12 and v13 is equal to 0. Okay, so what we'll do is impose the first element to be 1, and then the first equation tells you that you need a -1 over here, and if you have a -1 over here, the last equation tells you that you need a -1/2 over here. Okay, so that's my first eigenvector, and it's the eigenvector that corresponds to lambda 1 is equal to -1. Lambda 2 is equal to -2. So what we'll have here is, and you have to do the same thing, right? 0, -1, 0, 0, 1, 0, and 0, 1, -1. Okay, so I've injected lambda 2 is equal to -2 in here, and we'll have v21, v22, and v23 is equal to 0. So v2 is, well, the first equation tells you that the second element is 0. The last equation tells you that if the second element is 0, well, the third needs to be 0 as well, so we can inject a 1 over here. So that's our second eigenvector that corresponds to lambda 2 is equal to -2, and the third eigenvalue is -3. If we plug -3 in here, we end up with 1, -1, 0, 0, 2, 0, and 0, 1, 0. And the eigenvector is v3. We'll write it as v31, v32, and v33 is equal to 0. And v3 is, well, last equation tells you that the second element is 0. The first equation tells you that since the second element is 0, the first element is 0 as well. So here we'll have a 1 at the third component. So this is my eigenvector that corresponds to the eigenvalue -3. Okay, so what we can now do is construct the matrix V. Okay, remember that it's V1, V2, and V3. Okay, so that's equal to 1 minus 1 minus a half. We have 1, 0, 0, and 0, 0, 1. Right? And we'll have lambda is equal to -1, -2, -3, and that's equal to v minus 1 a v. Well, let us look at this first example in MATLAB. So this is the matrix A. This is the matrix V that we have obtained. We're going to compute v minus 1 AV. And what is done over here is, instead of using the matrix 1 minus 1 minus a half, and then 1, 0, 0, 0, 0, 1, we are going to use eigenvectors here which have a length of 1. So v1 here was 1 minus 1 minus a half. You know that if this vector is an eigenvector, then this vector is also an eigenvector. We simply multiply it by 2. Okay, this is also an eigenvector, and what we can do then is give a unit length to this vector. If we look at the length of this vector, so it's 2 squared plus 2 squared plus 1 squared, square roots, and this is equal to 3. Okay, so if we take a matrix now, where instead of taking this eigenvector, we take 2 divided by the length, 2/3, minus 2/3, and minus 1/3, and we leave the other eigenvectors the same. They already have unit length. Well, you have, well, a matrix V here with unit eigenvectors, and you'll see that if you use this matrix here and you'll compute V minus 1 AV, you'll obtain also the same diagonal matrix. And this is actually the command here in MATLAB, and MATLAB will generate this matrix over here. So let's run this code and let's have a look in MATLAB. And so this is the matrix. This is the initial matrix V that we have found in the exercise, and indeed if we compute V minus 1 AV, this is what we obtain. This is the matrix V with the first vector that has now unit length 1, and if we compute V minus 1 AV, again we obtain the same result, and this is what is obtained by MATLAB. You obtain the same eigenvectors, but you see here that the order of the eigenvalues is different. So let us take another example of a matrix that is given over here. We can compute the characteristic polynomial, so it's the determinant of A minus lambda I, and this is what you obtain. Here it's very simple. This matrix is upper triangular, so to compute the determinant you simply have to take the product of the elements on the diagonal. So this is the characteristic polynomial, and you see here that you have, well, an eigenvalue 1 that is a double eigenvalue, so it has algebraic multiplicity 2, and you have a third eigenvalue at 2. So we are in a situation where we might not have the possibility to diagonalize A, but we have to check. So remember that what we have to do is, well, look at A minus lambda 1 I times V1, and in our case here this is 0, 0, minus 1, 0, 0, 0, 0, 0, 1 times V1 is equal to 0. So you can see here that the rank of this matrix is 1. Okay, so this matrix has a rank 1, and if you look at the course of linear algebra, it means that, well, the rank of the null space of this matrix must be 2. So we can find 2 vectors, eigenvectors, that are independent. We'll find one for each of the 2 eigenvalues. Okay, so the first one will be V1 is equal to 1, 0, 0, and we'll call the second one V2, and this one will be 0, 1, 0, right? So in this particular case, so we are dealing with the case lambda 1 is equal to 1 and lambda 2 is equal to 1, we can find 2 independent eigenvectors. Okay, so let us now look at the situation where lambda 3 is equal to 2, and this will lead to minus 1, 0, minus 1. So we inject lambda 3 is equal to 2 in here, and we obtain 0, minus 1, 0, 0, 0, and 0 over here, times V3 1, V3 2, and V3 3. And in this case, what we can do, well, we can see that the second element must be 0, and if we fix the first one to 1, we need to take, by the first equation, the third one to -1. Okay, so in this case, if we stack the eigenvectors in the matrix, we have v1, v2, v3. We'll have the following matrix: 1 0 0 0 1 0 and 1 0 -1. Okay, and v -1 a v will be the diagonal matrix with the eigenvalues on the diagonal, and this will be lambda. So here we have a double eigenvalue, but we're still in a case where it's possible to diagonalize the matrix A. So let's check this second example in a MATLAB. So this is the matrix. This is the matrix V that we had obtained: 1 0 0 0 1 0, and then the last one was 1 0 -1. Okay, so if you compute the inverse of V A V, you'll obtain the diagonal form. So what is done over here is what we have done also in example 1. We can give the last vector v3 here a unit length, and then you'll have 1 0 0 0 1 0, and then 1 over the square root of 2, 0 -1 the square root of 2. And this will also work. Okay, v -1 AV will give the same diagonal matrix. This is what you obtain using the MATLAB command, and here you'll again obtain, well, eigenvectors that have been normalized to a unit length. Well, in the exercise we had used v1 is equal to 1 0 0 and v2 is equal to 0 1 0. And remember that we had a matrix that was 0 -1, 0 0 0 and 0 0 1 times v1 is equal to 0. So we had chosen these two eigenvectors, but we could have chosen, for instance, also v1 is equal to 1 0 0 and v2 is equal to 1 1 0. Okay, these are again two independent eigenvectors that obey this equation. So this is what we do over here. We have a v1 that is 1 0 0 1 1 0, and then the last column is 0 1 0 -1, that's v3. And if we compute v1 -1 a v1, we'll obtain again the same diagonal matrix. So let's run this code. And indeed we see that, so example 2, this is the matrix, this is the matrix V, the diagonal matrix. This is the example where we use the same matrix V but with the last vector v3 of length 1. Again, we obtain the same diagonal matrix. This is what is being generated by MATLAB. Okay, and this time it corresponds to what we have found. This is the v1 that we have used. Okay, it was different. Okay, but we still have two vectors v1 and v2 that are eigenvectors and that are independent, and again it generates the same diagonal matrix. So let us take another example here with this matrix A, And what we can do is again compute the characteristic polynomial. We compute the determinant of a minus lambda I. This is what you have to compute. This determinant you have to compute, and you see that the matrix is again upper triangular, so it's easy to compute the determinant. You simply take the product of the elements on the diagonal, and you see that you end up with a situation that is similar to the previous case. You have a double eigenvalue 1 and a third eigenvalue 2, so potentially it could be that it's not possible to diagonalize this matrix A. We have to verify. So let us look at the case lambda is equal to lambda, lambda 1 is equal to lambda 2 is equal to 1, and we compute A minus lambda 1 2I times V 1 2 is equal to 0. So this is equal to 0 1 2 0 0 3 0 0 1 times V1 2. Okay, so this eigenvalue is double, so we need 2 eigenvectors. But we see that this matrix has a rank 2. Okay, for the concept of a rank, refer to the other course in this teaching unit, Advanced Control 1, Linear Algebra and Applications, and therefore we know that the null space of this matrix will have dimension 1. So we can only find one vector such that this relation holds. So we will not be possible to diagonalize the system. So in this case, for this matrix, it's impossible to diagonalize it. So let's check this third example in MATLAB Simulink. This is the matrix that we have considered here, and we have seen that it's not possible to diagonalize it. It is, however, possible to bring it into the Jordan form using an adequate similarity transformation that is given here. So how you find this V goes beyond the scope of this course, but you will see that when you do V minus 1 AV, you'll obtain a matrix in a Jordan form, and you can kind of see what this form will be, because you know that the eigenvalues were 1, 1 and 2. So you'll have a 1 over here, so you'll have a Jordan block over here, and all the rest will be zeros, right? So this is what we expect. And if you compute the eigenvalues and eigenvectors using the I command of MATLAB, you will see that the result is wrong. So if you use this command on a matrix that is not diagonalizable, the results are wrong, and you should keep this in your mind. So let's run this code, and this is what you obtain. So this is the matrix, this is the matrix V, the similarity transformation that will bring A into the Jordan form, and you can see here indeed that you have the correct form, and this is a Jordan block. Okay, and if you look at what is produced by MATLAB, well, it arrives at a form that is diagonal, but you can see that it is wrong over here, because you have two eigenvectors that are the same. Okay, so really in the case of a matrix A that is not diagonalizable, the results that are produced by MATLAB are incorrect. So what you can do now is, well, illustrate all those methods to compute the exponential of AT on this particular matrix. So the first method, if you remember, is the Laplace transform method, and the exponential of at can be computed as the inverse Laplace transform of, well, si minus a inverse. So obviously we have to be able to compute si minus a inverse. So that's the inverse of s plus 3 minus 1, 0 s plus 2 inverse, right? So it's 1 over the determinant, so it's 1 over s plus 3 s plus 2. What we'll have to do is exchange these two and change the other ones. We change sign, and we have then s plus 2, s plus 3, we have a 1 over here and a 0. Well, if this is new to you, you should consult the associated course of linear algebra and applications, because inverting a 2 by 2 matrix should come very naturally at the end of this teaching unit, Advanced Control 1. Okay, so what we have here is 1 over s plus 3. Here we have 1 over s plus 3, s plus 2. And here we have 1 over s plus 2. Right, so now the exponential. This one, by the way, you can rewrite it, because we'll have to take the inverse Laplace transform. So we have to take the partial fraction expansion, right? And if you do that, and I'll leave this as an exercise, it's 1 over s plus 2 minus 1 over s plus 3. You can see that if you put everything on this under the same denominator again, you'll have s plus 3 minus s plus 2. So this is correct, right? So now we want to obtain this exponential, and we have to do the inverse Laplace transform of this matrix over here. And that's pretty easy. We end up with e to the minus 3t, e to the minus 2t minus e to the minus 3t, 0, e to the minus 2t. And there's your expression of the exponential of at. Well, notice that to use this method, you have to be able to compute the inverse of a matrix, and you have to be able to compute inverse Laplace transforms, and also to do partial fraction expansions. So what you can do now is use the second method, and it's the method of the Jordan form, or maybe a better name is the diagonalization method, as we will always have matrices or tackle matrices that are diagonalizable. Okay, so the first thing that you have to do, and this I have already prepared, is compute the eigenvalues, eigenvectors. So you compute the determinant of a minus lambda I. This yields the characteristic polynomials, and you look for the roots, and here you have two roots. Lambda 1 is minus 2 and lambda 2 is minus 3. Then you have to look for the eigenvectors. Okay, so they are the solution of this type of systems of equation, and here are the two eigenvectors. And then you know that you can write a as v lambda v minus 1. Okay, v, well, you simply stack the vectors next to each other, and this will yield 1 1 1 0. Okay, and lambda, that's simply a diagonal matrix with the eigenvalues on the diagonal. What we'll need here is, well, v minus 1. So v minus 1, it's 1 over the determinant, so it's 1 over minus 1. And then we have to swap these two and change the of sign. So we have 0, we have a 1, and we have a minus 1 here. So because of the minus 1 here, we have 0, 1, 1, minus 1. Okay, and we know that the exponential of at is v e to the lambda t v minus 1. Okay, so this will be 1. So we have to take v here, 1, 1, 0. The exponential of lambda t, that's quite easy. We have to take this matrix, and on the diagonal we'll have e to the minus 2t and e to the minus 3t. E to the minus 2t, e to the minus 3t, 0, 0, and then we have to multiply, okay, by this matrix over here. So let us do first this multiplication here. So we'll have 1, 1, 1, 0, and then if we start to multiply, we have a 0 over here, we have e to the minus 2t over here, we have e to the minus 3t over here, and we have minus e to the minus 3t. And if we continue, well, we have e to the minus 3t. Here we have e to the minus 2t minus e to the minus 3t. Here we have a 0. And here we have e to the minus 2t. And this is indeed what we had obtained with the previous method. We can now use the third method, which is the Cayley-Hamilton method. Again, we need the eigenvalues, but in this case we do not need the eigenvectors, so you don't need to compute them. And remember that we'll consider a function f of lambda, which is e to the lambda t. We will consider a polynomial function in lambda, alpha 0 plus alpha 1 lambda. Well, there will be 3 eigenvalues if we impose that f lambda is equal to g lambda on the spectrum of A. There will be 2 constraints, so it's enough to take a polynomial that is of degree 1, that is n minus 1, where n is equal to 2. Okay, so let us impose that f lambda and g lambda are equal on the spectrum of A. This leads to the following constraints. We have f of minus 2, that's e to the minus 2t, is equal to g of minus 2, and that's alpha 0 minus 2 alpha 1, and that's equation 1. We have a similar equation for the second eigenvalue, is equal to g minus 3, and this is alpha 0 minus 3 alpha 1. Okay, so if we do 1 minus 2, we'll see that alpha 1 is e to the minus 2t minus e to the minus 3t, right? If we do 3 times 1 minus 2 times 2, we'll see that alpha 0 is 3 times e to the minus 2t minus 2 times e to the minus 3t. Okay, so this is how we obtain alpha 1 and alpha 0. So g of lambda is now defined, and we know that because of the Cayley-Hamilton property that fa, that's e to the at, is equal to g of a. So that's this thing here where you replace lambda by the matrix E, and when there is no lambda you have to introduce this identity matrix. So that's alpha 0, that's 3e to the minus 2t minus 2e to the minus 3t times the identity matrix plus, that's alpha 0, plus e to the minus 2t minus e to the minus 3t, and that's alpha 1 times a. If you compute this, you'll have 3e to the minus 2t minus 2e to the minus 3t, that's coming from this one, and then you'll have minus 3 e to the minus 2t minus e to the minus 3t, right? This is coming from this one. So you can see here that this one and this one will cancel out, okay, and what we'll have here is e to the minus 3t. Okay, so for this term over here we only have to take what is coming from here, and it's a 1 over there, so we have e to the minus 2t minus e to the minus 3t. Okay, so again for this one it will not contribute for this element, and here we have a 0, so we have indeed a 0 over here. And for this one here we have this one here again, 3e to the minus 2t minus 2e to the minus 3t minus 2 times e to the minus 2t minus e to the minus 3t. Okay, and you will see now that, well, these two cancel out, and you have here e to the minus 2t. Okay, so indeed we obtain e to the minus 3t, e to the minus 2t minus e to the minus 3t, 0, e to the minus 2t, and you see here that we indeed obtain the same thing that we had obtained with the two previous methods. So we can have a look at computing a power of a matrix. So here we'll compute a to the power n. We could have used also this diagonalization method, but here we'll use the Cayley-Hamilton method. We remember that the eigenvalues are -2 and -3. So what we'll do is use a function f of lambda, and now it will be lambda to the power n. We still use the same polynomial g lambda. There are two constraints, so it's enough to use a polynomial of degree 1 because it has two coefficients. Since there are two constraints, that's okay. And we have to ensure to impose that f lambda and g lambda are the same on the spectrum of a. So f of -2, that's -2 to the power n, is equal to g of -2. This is alpha 0 -2 alpha 1. This is equation 1. F to the -3, that's -3 to the power n. That's g of -3, and this is alpha 0 -3 alpha 1. So if we take the first one minus the second one, we obtain that alpha 1 it's -2 to to the power n minus minus 3 to the power n, right? And if we do 3 times 1 minus 2 times 2, we obtain that alpha 0 is 3 times minus 2 to the power n minus 2 times minus 3 to the power n, right? And an, so fa, that's a to the power n, is equal to g of a. So this is 3, and this is what I'm writing here is alpha 0. This is alpha 0 times the identity matrix plus the parameter alpha 1 times a. And if you go through the calculations, same kind of calculations as in the previous example, you will see that an is equal to minus 3 to the power n minus 2 to the power n minus minus 3 to the power n. We have a 0 over here and a minus 2 to the power n. In fact, we can use the Cayley-Hamilton method to compute any function of a matrix, and what we'll do here is compute the sign of the matrix A. And of course, since I don't think there are really applications for that, this is only for your information. So what we'll do is use the same trick. So f of lambda is now the sign of lambda. G of lambda is still our first order polynomial, alpha 0 plus alpha 1 lambda, 2 parameters, and there are 2 constraints, and f of minus 2, which is the sign of minus 2, is equal to g of minus 2. That's alpha 0 minus 2 alpha 1, and this is equation 1. F of minus 3, what we are doing here again is imposing that the two functions are equal on the spectrum of A. Sine of minus 3 is equal to g of minus 3. This is alpha 0 minus 3 alpha 1, and this is equation 2. If you do 1 minus 2, we have that alpha 1 is equal to the sine of minus 2 minus the sine of minus 3. And if you do 3 times 1 minus 2 times 2, we obtain that alpha 0 is equal to 3 times the sine of minus 2 minus 2 times the sine of minus 3, right? So f of A, that's the sign of the matrix A we're looking for, is g of A, and this is, well, 3 times the sine of minus 2 minus 2 times the sine of minus 3. This is alpha 0 times the identity matrix plus sine of minus 2 minus sine of minus 3 times A, and this is alpha 1. Again, if you go through the calculations, you'll see that the sine of A is equal to the sine of minus 3, the sine of minus 2 minus the sine of minus 3, and the sine of minus 2. So what we can do is check, for instance, the computation of A to the power n. This is what we had obtained when we did the calculations, and here is the computation using MATLAB, and this is the sign of the matrix that we had obtained, well, by hand calculation. In order to obtain the sign of a matrix, you have to use this command fun_m, so fun matrix, and this will compute the correct way of obtaining the sine of A. If you do simply sine of A, what it will do is, well, simply compute a matrix with the sine of each element. So this one is wrong over here. So let's have a look and compute the code. And you can see here that this is what we had obtained, and this is what is obtained by MATLAB. This is the sine. This is what is obtained with this fun m function, and this is what is obtained with the sine function. As you can see, it computes the sine of each element. So this computation here is wrong.